again. So I will teach you this course kinetic processes in material. And I am Nguyễn Hồng Hải. My name. I am from Department of Foundry Material and Technology. Okay. So to study this course, we can use this textbook. Very good book. Phase transformation in mechanical law. Okay. Trả lời tí nhé. This phase transformation in mechanical alloy of Potter and Easterling. Very good book. I think you can download this book from internet. And it is my book, Kinetic Process in Material. It's a main textbook. And for the DT, you should attend the class more than 80%. Homework 100% and lab work 100%. For assessment, for midterm exam, it will be 30% of the total score, total year score. Okay, homework problem and independent laboratory project, and finally the final exam. It consists of 70% of the total score. It's an assessment. So the content of our course principally for part. First one, the review of the thermodynamic, then diffusion, then surface interfaces, and finally the phase transformation. I will teach you almost, but at the end, Professor, the teacher Triển will take some lecture. Okay. So, firstly, we classify the matter by the state. You know, the matter can be exist in 3 main states: liquid, solid, and gas. Liquid, solid, and gas. Okay. And then now there are states. It's plasma. One more state. Plasma. So, but the main state of the matter: liquid, solid, gas. Only solid can be considered as a material. Only solid. Liquid and gas are not material. Only solid. So for solid we have inorganic and organic. Inorganic and organic. For inorganic we have metal, glass, ceramic. And for organic, we have polymer, wood. So only this, it can be considered as a material, only solid. So to make a material, we have to transform liquid and gas into the solid. It is the phase transformation. And it is a material cycle. So from the raw material of the earth, we can have some raw material, and by synthesis and processing, we make material, inert material. And from this material, inert material, we make the product. We can use in industry, in our conventional life, so on. And then we use this product. After this, maybe some waste, so it is returned by recycle to the synthesis and processing. So the cycle is growth like this. Maybe some was return into the earth. Okay. So your task here, processing to make the material. Yeah, from raw material. Make the inert material by synthesis and processing. So it is our field of study and activity. So here you can see some feature, some aspect of the material. So from the chemical composition, we do composition, and by synthesis and processing, we make the material. We transform gas, liquid, and solid to material. It's a phase transformation process. Okay, and this by composition and synthesis processing, you can make the material with the desired structure and microstructure. And this in the structure and microstructure of material in determine their properties and performances. So we have the main feature of material composition and synthesis and processing. This will determine the structure. Structure determines the properties and performances. And yeah, we can see in this picture, you can see the physical space of material. So we begin from chemistry, from chemical composition, chemistry. You can see here 5 cycle. In at the center, we have a chemistry or chemical composition. From this chemical composition, the see that about 70% of the trend come from chemical composition. 70% of the trend of material, of alloy metal, and something like that. 70% come from chemical composition. So the rest of 30% come from processing. Processing include something like crystallization, solidification, deformation, heat treatment, and so on. It is a processing to make material, but inert material, and this in 30% of strength. But we never reach the 100% strength of the alloy. Never, not yet. We tend to reach it, but has the present nowadays have not reached the 100% of the trend of material. We will try to do this. Okay. So, beginning from chemical composition, via the processing, we make the material with desired structure and microstructure. What is the microstructure of the alloy? It is the size and morphology of the grain, size morphology of the grain, crystal grain, and lattice defect. So mainly size and morphology of the grain. Grain can maybe fine, maybe coarse, maybe fine, maybe coarse, and morphology of crystal, maybe then dry, thick, and so on. So this is the microstructure of an alloy, and this microstructure and structure determines the trend, the properties, such as strength, hardness, ductility, elongation, and so on. So the trend, and finally performances. For example, fatigue, grip, corrosion, and wear resistance, and so on. Is related with the environment. These performances. So we have a 5 cycle. The physical space of a material consists of 5 cycles like this. At the center, we have chemistry, then processing, structure, properties, and performances. So, and correspondingly to this physical space of material, we have this very strongly related environment. So, correspondingly to this physical space of material, we have the MSc subject, material science and engineering subject, like thermodynamic, kinetic, crystallography, property performances. So, we have the 5 cycle corresponding to this physical space of material, and our subject, our course, kinetic process in material, belongs into this kinetic processing and kinetic. So we have kinetic process in material. Okay, is a relative position of our course, and you know that the difficulty increased towards the center. The thermodynamic is very our course is rather difficult. Thermodynamic is the most difficult. Okay, so we have the physical space of material. Chemistry, processing, structure, property, performance. So the outermost cycle, the performance characterize how material behave in the given environment, how the material behave, and this strongly related is the environment, the outermost cycle. And then the performances realized by the set of the properties in the second cycle. Okay. So the properties are achieved by the agglomeration of the phases, its various structure. Okay. So this property can be achieved by structure. And the morphology is the third cycle. And structure obtained through the proper processing and the chemical composition, accurate chemical composition. So the chemistry composition determines the structure. Structure determines the property and performances. So processing is very important step in the making of material. It determines the structure of material. Methanol alloy. See. So our course kinetic processing is the second cycle. Yeah. And why the two outmost cycle, performances and properties, is are very strongly related is environment. The three, no, this one, chemistry, processing and structure, or thermodynamic, kinetic, crystallography. They are the key component of material science and engineering. Three key components: crystallography, kinetic, and thermodynamic. Okay. And thermodynamic and kinetic are viewed as a difficult subject. So we have three key components of material science and engineering: thermodynamic, kinetic, and crystallography. And here we have the representation of the material. See, the scientist study the relation between the structure and properties. Scientist and engineer study the relation between the processing and performances. See? So different aspect of the material processing. Structure, property, processing, and performances. Okay. So it's some introduction to the material. So we now turn on the thermodynamic. Chapter 1, thermodynamic. So the main use of thermodynamic in physical metallurgy is to allow the prediction of whether an alloy is in equilibrium. Whether an alloy is in equilibrium. Equilibrium is the most important in the thermodynamics. The alloy or the system is in equilibrium or not. We have to answer to this question. Equilibrium. And in considering the phase transformation, we are concerned with the change towards the equilibrium. If some system, some alloy is not in equilibrium, so they will change. They will change their structure, microstructure, and so on towards the equilibrium. Okay. And for this, thermodynamic is very powerful tool. But the rate at which equilibrium can be reached cannot be determined by thermodynamic alone. So we need the kinetic processes. The kinetic process will allow us to know how quick the equilibrium can be reached. It's a kinetic process. The equilibrium, the thermodynamic allow us now only whether the alloy is equilibrium or not. But thermodynamic do not allow us to know how quickly the system can change towards the can reach the equilibrium. It belongs to kinetic processes, not thermodynamic. How quick? Okay. So the main question of thermodynamic is if the system is in equilibrium. The main question of thermodynamic. If the system, the alloy, the phase, and so on, is in equilibrium. Okay. So what is the system? System is a mixture of the one or more phases. Maybe one phase can consist an system, but maybe more phases. So system is mixture of one or more phases. For example, you have the aluminum silicon alloy, aluminum silicon system. Okay, it is a phase diagram, aluminum silicon phase diagram. We have a aesthetic here. So in this system, we have two phases, aluminum and silicon. So this system is a mixture of two phases, and we have a hypothetic alloy. It's a aesthetic composition. It's about 12% of silicon. About 12% of silicon. So before this composition, we have hypothetic alloy. For example, alloy A356 with about 7% of silicon. So for this system, for this alloy, we have the microstructure like this. We have a primary aluminum like this. It's dendrite. In the format dendrite. And we have the plus the aesthetic. See, primary aluminum plus aesthetic. Aesthetic it is the silicon in dark embedded in the aluminum like this. Okay. So here we have the primary aluminum by we have silicon, authentic silicon. It's the composition, chemical composition is hypoauthentic. Mainly we have the, for example, we have 7% of silicon for this alloy A356. We have this microstructure. So you have another chemical composition. For example, this alloy A390. So this alloy possesses 18% of silicon, much more silicon than this one. This only 7. Here we have 18. So for this alloy, the microstructure will be quite different from this one. Quite different, like this. So instead of primary aluminum, we have the primary silicon in this form, and plus aesthetic structure. Okay. So you can see the difference between the two alloy because of the different composition. And if we have the authentic alloy, about 10% of the silicon, for example, the alloy A413, so we have the structure is authentic. So we have the silicon in dark embedded in the aluminum, that is in white. It's an authentic structure, consists of two phases, silicon and aluminum. You see? So authentic is not the phase, it's not the structure. It's the structure, not phase, but structure, because there are two phases here. You see? So, for example, for this aluminum and silicon system, we have quite a different microstructure depending on the chemical composition. Hyper-authentic, and authentic. Absolutely different microstructure. The system. So system is mixture of one or more phases. It's a system. So what are the phase? What is the phase? Phase. We have the primary aluminum phase, primary silicon phase. So the portion of the system whose properties and composition are homogeneous, and which is physically distinct from the other part of the system. It is the phase. So there are two features of the phase. Properties and composition are homogeneous. The same properties and composition everywhere. The same. And physically distinct from the other part of the system. By, for example, by this in this system, by grain boundary, by interface between the aluminum and authentic, distinct from the other part of the system, mainly by surface, the grain boundary, and by interface between phases. Is the phase. So you should remember what is the phase. Two features. First is the property and composition are the same everywhere, homogeneous, and physically distinct from the other part of the system by the boundary, by the interface. It's the phase. So in this system, you have two phases, aluminum and silicon, and they distinct pattern. Okay, you can see silicon or aluminum absolutely distinct from authentic structure. Okay, it is a phase. So we have the example of this alloy A390. It's 18% of silicon. So we have this microstructure of the hypothetic aluminum silicon alloy. This one. So we can see the primary silicon. Platelet gray, platelet like this. Very coarse, very harmful. It's very coarse. You see. And you have the authentic. Authentic, it is a fine silicon platelet embedded in the aluminum like this. It's pathetic. So if the primary silicon is so coarse, very coarse, so it is very harmful, and the mechanical properties of this alloy is not high. Not high. We we have to make this primary silicon finer. Is the undesired microstructure, because the primary silicon is very coarse, and so the mechanical properties not high. So we tend to have this microstructure. This primary silicon finer, like this. And this desired structure. So the question: how to make this microstructure from this one? How to make the primary silicon finer? It's by processing. And by this we can improve the mechanical properties of the alloy. But what processing and how to do is another question. But to make this to make the primary finer silicon finer, we have to apply some processing, some technology, some technique to have it. Okay. This is the role of the processing. This processing allows us to have the desired microstructure to improve the properties of the alloy, of the material. Okay, that is why you need the modern, the recent processing process. Why you need to apply the technology, high technology, and so on. So, okay, this is the example of the change of the size and the morphology of face. So the next thermodynamic term is component. Component it is the different element of chemical compound which make up the system. Maybe the element, maybe chemical compound. It's also component. So for example, we have the iron carbon system. You know this phase diagram. Iron carbon phase diagram. But instead of carbon, you can use cementite as a component. So in this phase diagram, we have the two components: iron as an element and cementite as a chemical compound. So element or chemical compound can be the the component of the which make up the system. This component and the composition of a phase of the system can be described by giving the relative amount of each component. For example, if the content of the carbon is less than 2%, you have the steam. And steam is limited here from 2%. And if the content of the carbon is more than 2%, we have cast iron. Okay. So the composition of a phase of the system can be described by the giving the relative amount of each component. And the component is the element of chemical compound. Okay. So the phase transformation. One or more phases in an alloy or in system, alloy is a system, change into new phase or mixture of phases. It's a phase transformation. One or more phases, maybe one, maybe more phases in an alloy, change into the new phase or mixture of phases. It's phase transformation. For example, we have this also aluminum silicon system, and there are some iron. So we have intermetallic compound like this, and it is a beta. Aluminum 5, iron and silicon. They have the platelet form like this, and very harmful. Very harmful. It's undesired microstructure. It's intermetallic compound. See, beta, aluminum 5, iron and silicon. Very bad microstructure, undesired. This is more desired. You have also the intermetallic compound, but in the form of alpha. And you have the chemical formula as aluminum 8, iron 2, and silicon. And they have the fixed bond or Chinese script form, and the less harmful. It is desired, more desired than this one. For the aluminum, silicon, and iron system. In this system, we have 3 components: aluminum, iron, and silicon. You see, we have to make this microstructure instead of this one. It is very harmful. This one is much better because the intermetallic compound, aluminum, iron, and silicon have a fixed bond of Chinese is more compact than this one. But this is stable. This is stable. This is not stable. Unstable. So because this is unstable, so this structure microstructure will transform to this one. Because this is stable. See, the desires transform to undesired. So we have retained this microstructure by application some technique. Okay. So the question now: what determines the stability of the phases? Why this phase alpha is unstable and this phase beta is stable? Why? What feature? What determines the stability of phases? So at constant temperature and pressure, the relative stability of system is determined by the gift free energy. By gift free energy. And we have the formula to calculate the gift free energy. Z is the gift free energy equal to S minus Ts. S is the enthalpy. Enthalpy is the measure of the heat content of the system. Enthalpy. Normally, enthalpy is equal to E plus PV. here E the internal energy of system, V pressure, and V is the volume of system. Okay, so enthalpy equal to internal energy plus PV. But in general, for condensate surfaces as solid and liquid, the PV term is very small. This one is very small in comparison with the internal energy. So we can say that enthalpy is approximately equal to the internal energy. You can do this. Is approximately equal to it because this term PV is much smaller than this one. Okay. It is S in the free energy equation. Enthalpy. T is absolute temperature, and it unit is the Kelvin degree. And S it is the entropy of system, the measure of the randomness of the system. Randomness. So you see the enthalpy is measure of the heat content, and entropy is the measure of the randomness of the system. So the stability of the system is determined by its deep free energy. And deep free energy can be calculated by this equation 8 minus Ts. And you have the from above you have the intensive properties. It means this in property is independent on the sign of the system. It's temperature and pressure. They are independent on the sign of the system. It's the intensive properties. When they have extensive properties, they are directly proportional to the quantity of material in the system, and this it is the volume, internal energy, enthalpy, entropy, free energy, free energy. So we distinguish intensive properties independent of the sign of system, temperature, and pressure, and you have extensive properties. Okay. So the system is said to be in equilibrium when it is the most stable state. And stability is meant by this, by free energy. Okay. So a constant temperature and pressure, a closed system. Yes, so one system of fixed mass and composition is a closed system. In the stable equilibrium, if it has the lowest value of the free energy. Okay. If the free energy is lowest, so we have the stable equilibrium, the phase, the system in the stable equilibrium. If they have the lowest value of the free energy, or in the mathematical term, you can write DC is equal to 0. Yeah. DC is equal to here or maybe here. It minimum in the energy curve, free energy curve of the system, depending on the arrangement of the atom. See? So here we have the minimum in free energy in here also. So in mathematical term, you can write D3 equal to 0 at minimum. So here we have the unstable. Only in this position, this arrangement and this one, it is stable. The rest is unstable because DC is not zero. The derivative of the free energy is not zero. See? So we have the here. It's stable and maybe here. But we have this one it only metastable. Metastable. Not not the real, not true table, but metastable. Because the energy of this system is a minimum in comparison with some arrangement around it. But this still higher. The free energy of this system still higher than some other system unstable. You see, the free energy of this system is higher, so it is not absolute stable, absolute equilibrium, because the free energy is still high, so it is a metastable only. And here we have the true equilibrium, the stable here, absolute stable, because the free energy is the minimum, lowest here. See, so we have the stable. For example, in the case of carbon, the stable form of the carbon is graphite, and metastable form of the carbon is diamond. So you see the pressure and temperature diagram of the carbon. So here graphite can exist at this temperature at relatively low pressure. Diamond the temperature is also like the graphite, but pressure is much higher than cement. See the three state of three form of the carbon: graphite, diamond, and very high temperature to maintain the carbon more than 4,000 degrees Celsius. So formally, we know only two forms of the carbon, it is graphite and diamond. But nowadays we know one more form of the carbon. It is a fluorine. In discuss about this in the other course. So now carbon can exist in the form graphite, diamond, and fluorine. Okay. So graphite is stable form of carbon. Diamond is metastable form because they have very high free energy, and with the time, the from this equation we can conclude that the state with the high stability will be that with the low enthalpy and high entropy. Low enthalpy and high entropy, so free energy will be low. And if this free energy have the lowest value, so we have the stable system. Okay, so the system with the state with the higher stability, that is low enthalpy and high entropy. So they will be stable. If the state with high entropy and low entropy, high enthalpy and low entropy, we have unstable state. State it is the arrangement of atoms. And from you see from the unstable state, the system can transform to the stable. But before this, the energy of system must be increased a little bit. You see, before transform from the metastable state to the stable state, the system have increased their energy a little bit. This one. And we can say that they must be activity. The atom, if they tend to move from the unstable or metastable arrangement to stable arrangement, they must be activities. We have to supply some energy to them, to atom, so that they could transform, they could move, rearrange from the metastable to stable state. So it is stable. So stability of the system is determined by deep free energy. And deep free energy can be calculated as enthalpy minus T multiplied by entropy. The lower free energy, the more stable the system. Okay. So any transformation from the system from the higher energy system with higher energy to the system with a lower energy, from unstable or metastable state to the stable state. Reason is the decrease in the gift energy. Any transformation that reason in the decrease of gift energy is possible. Okay. In another word, the transformation, any transformation is possible if the free energy will decrease after transformation. Okay. So the necessary criterion for any phase transformation is the delta C, the chain is energy, chain of free energy before and after transformation must be less than 0. Z3, Z2 is less than Z1. So Z2 minus Z1 is less than 0. The decrease in free energy. So the transformation can be only possible if the free energy decrease after transformation. It's very the most important criterion for phase transformation. And here's the delta C. The difference in free energy between two states. So the answer is the condition for phase transformation. And the question, how fast does the phase transformation occur? So belong to the realm of the kinetic. This one, this answer to this question belong to the thermodynamic. And the answer to this question, how fast the rate of the transformation belong to the kinetic. So the usual way to measure into size of the system is by the number of the mole. The number of the mole. You can measure the size of the system by the calculate the number of the mole of the material it contains. Okay. So the extensive properties are then molar quantity. Per mole. Enthalpy per mole, entropy per mole, free energy per mole, and so on. Okay. Expressed in unit per mole. And the number of mole, this one, number of mole of the given component, iron or cementite in the carbon iron carbon system, or aluminum or in silicon in the aluminum silicon system. So the number of mole of the given component in the system is given by the mass of the component in gram divided by its atomic or molecular weight. We divide the mass of component by the atomic or molecular weight. So we have the number of mole of the given component. If the given component is an element such as iron, aluminum, or silicon, so it's divided by the atomic weight. So if the component is for example cementite, so we divide this mass to the molecular weight. It depends on what is the component, the element or the chemical compound. Okay, so we can calculate the number of mole. Okay. By division of the mass component by atomic or molecular weight. And the number of atoms or molecule within 1 mole of material equal by Avogadro number. And this Avogadro number is equal to 6.03023 multiplied by 10 power 23. See, it's the Avogadro number, the number of atoms or molecule within 1 mole of material. So we have this very big number. You can this number. So it is the Avogadro number. So we have another term of the thermodynamics, such as mole, molecular weight, atomic weight, Avogadro number. So okay, this is some feature of the equilibrium. Some feature of thermodynamics. And we turn now on the single component the system. Only one component in the system. It is single component. So the single component system this system which contain the pure element or one type of the molecule. Maybe pure element, maybe one type of molecule that does not dissociate over the range of the temperature of interest. Okay. So it is a single component system. This contain only pure element or one type of the molecule, and this does not dissociate over the range of temperature of interest. For example, we have this example of carbon dioxide. Carbon dioxide pressure temperature phase diagram. See, showing some trick point and critical point of carbon dioxide, and we have in this range of temperature and pressure we have only gas. Here we have solid in red, and we have liquid and supercritical fluid here. Yes, so it is a single, only one molecule carbon dioxide. Okay. So in order to predict the phases that are stable or mixture that are in equilibrium, we say the phase stable or the mixture of phase, the system are in equilibrium. At different temperature, it is necessary to calculate the variation of free energy with temperature. Okay. Should to pay your attention. That's the phase. The phase are stable. We say the phase are stable. Phases are stable. The mixture are in the equilibrium. The system is in equilibrium. Okay. Because the system is the system, the alloy is a mixture of some phases, and we have to answer on the question if these phases are in equilibrium. Okay, so we say that phase is stable and the system is in equilibrium. We do not say the phase. One phase is in equilibrium because the equilibrium it is much have some phases. This one phase it is not in equilibrium. It is stable. So phase stable and mixture of phases or system is in equilibrium. Okay. But please do not say phase in equilibrium. One phase, maybe phases are in equilibrium. Okay. So we have some introduce some other thermodynamic term. The specific heat. Firstly, is the quantity of the heat in joule required to raise the temperature of the substance by 1 degree Celsius. The heat we have to supply to the substance to increase heat temperature by 1 degree Celsius. It's a specific heat. Okay. We have the specific heat by definition. We can write in the mathematical term. We can write C. It's a specific heat is equal to the derivative of enthalpy. It's a heat because heat enthalpy is measure of the heat of the system. So it is the first derivative of enthalpy with respect to the temperature at constant P, at constant pressure. Is the specific heat. The quantity of heat expressed by enthalpy. We have to supply to the substance to increase its temperature by 1 degree Kelvin. It's specific heat. And we can plot the graphic like this. FCP, the coordinate, and temperature on the axis. Coordinate axis. We have this specific heat curve for single component system. And then we have the variation of enthalpy. Variation of enthalpy is with temperature can be calculated by the integrating this equation. If we integrate this equation, you can find the variation of the enthalpy. In mathematical term, we have S from the integrand from the temperature to temperature of interest of Cp dt. Okay. So it's a graphic. The enthalpy curve versus the temperature. And the slope at this curve is the specific heat slope. And at this temperature, 298 degree Kelvin, the enthalpy is zero. So we have the enthalpy. And then the variation of the entropy with temperature can also derive from the specific heat. And taking the enthalpy at 0 degree Kelvin as 0. So the entropy of any system at 0 degree Kelvin equal to 0. From 0 Kelvin to temperature of interest of the ratio between the Cp over T dt. And we have this curve, entropy curve versus temperature. The variation of specific heat, enthalpy, entropy with temperature. On the axis, we have always temperature. So we have very important thermodynamic term such as specific heat, enthalpy, entropy. You can calculate. You can plot the graphic versus temperature. So we have the example. Okay, we have an example. The specific heat of the solid copper above 300 degree Kelvin is given by this equation. The specific heat of the solid copper Cp is equal to 22.64 plus this 6.38 multiplied by 10 power minus 3 T Joule per mole per degree. So the question, by how much does the entropy of copper increase on heating from 300 degree Kelvin to this one, 1358 degree Kelvin. This is the melting temperature of the copper. This one. It's the room temperature. So by how much the entropy of copper increase change if you heat from the room temperature to the melting temperature. The question. It's easy to solve. We have the chain of the entropy. Can calculate by this one. Integral from T1 to T2 of this, and we substitute this equation to this one, to this integral Cp to this one. You can find the chain of the entropy. Okay, we apply this equation. Okay, so we substitute this to for Cp here, and the temperature from T1, it's the room temperature to melting temperature from this to this one. And we take the integral. This is easy to take, and we substitute the value of temperature to this T. See, easy to solve. When you have the answer at 40.83 joule per mole per degree. Easy to do. So the answer on heating from the 300 degree Kelvin to 1358 degree Kelvin, the entropy of copper increase by this amount, 40.83 joule per mole per degree. See? It's a very easy task. Okay, and we can finally we can find the variation of heat free energy. This is the most important with temperature. We have the variation of the heat, specific heat, of enthalpy, of entropy with temperature. That's the most important. It is the variation of the heat free energy with temperature. And this variation can be obtained by the combining the this figure, this one, enthalpy, entropy, and using this equation. S3 is equal to S minus Ts. S here. You combine this enthalpy curve with the entropy curve, and this with this equation, you can find the heat free energy. See? And you can plot the free energy of the different phase. For example, in this enthalpy curve and minus Ts. Here, you can obtain the free energy. We have the curve. We do the minus here. See, so we have the distance between the enthalpy curve and free energy curve. This one, it is a Ts. And slope of this free energy curve is minus S. Here, minus S. So you see, we can compute the free energy curve from the enthalpy, entropy curve, and this equation. We combine these three elements, and we can find this. And you can see that the free energy curve, free energy of system decrease with temperature. The higher temperature, the lower frequency of system. Very important conclusion. The frequency of system decrease with temperature. So we have this C equal to 8 minus Ts. Give frequency. And C decreases increasing T. And the rate of decrease given by minus S. So I can say that the slope of this curve is minus S. Okay. The slope of the enthalpy curve is a specific heat. And slope of the frequency curve is minus entropy. Minus because it decrease. The frequency decrease with temperature. Here the slope is positive because the enthalpy increase with temperature, but frequency decrease. So we have the slope minus here. Minus. See? So, okay. Do you need some rest? Do you need some rest?
Yes.
You will have some small break?
Yes.
Okay. 10 minutes? Okay, 10 minutes?
Yes.
Okay. So we have a small break. We have some rest before continue. Okay.
Em thưa thầy,
Ừ.
thầy có thể up luôn slide lên bây giờ được không ạ? Tại vì lúc nãy em ghi nó không kịp, thầy tua hơi nhanh.
Thầy sẽ up lên.
Rồi, thầy up luôn bây giờ được không ạ?
Để làm gì?
Để em vừa xem slide cho nó dễ ạ.
Em quy ra được không? Rồi thầy up luôn. Ok, no problem. Alo, mình tiếp tục nha. Continue. Alo.
Dạ vâng ạ.
Đây, còn có 9 bạn ở đây thôi thế này. Nguyễn Mai Nguyệt Quế đi đâu rồi? Bạn Nguyễn Mai Nguyệt Quế đâu rồi nhỉ? Không thấy á? Chạy rồi à? Nguyễn Mai Nguyệt Quế tí nữa các bạn bảo Nguyễn Mai Nguyệt Quế báo cáo lại thầy tại sao tiết 2 để bỏ đi đâu nhé. Ok, continue. Ok. So we have a give frequency, and we have like this. You can compute the frequency curve like this. So you can compute the frequency curve of liquid like this. The enthalpy curve of liquid and frequency curve C of liquid, and that of solid. The frequency curve of solid and frequency curve of enthalpy curve and frequency curve of solid. And as the melting temperature, this F6 temperature. So as the melting temperature, the frequency curve of the solid and liquid are equal, each to other. They are equal. So we can say that this is the equilibrium temperature. Okay. So as the Tm, as the melting temperature of the alloy, both liquid and solid phases have the same value of the C. This curve intersect, and we have the intersection, and they have the same frequency, the same value. So you can say the solid and liquid are in the equilibrium. It means they exist in equilibrium because their frequency are equal. So you can say Tm, the melting temperature, the equilibrium melting temperature as the pressure concern. Okay. So this melting equilibrium temperature. So at this temperature, the heat supply to the solid, to the system, will not raise the temperature, will not increase the temperature, but supply the latent heat that required to convert solid to liquid. This interval BC. So at the temperature, if you supply the heat, the energy to the solid, so heat temperature do not increase. Heat temperature remain at the same value at Tm, but it convert from the solid state to the liquid state, and this is the latent heat of melting this interval BC. Okay. So it means the latent heat of the melting L is equal to difference in enthalpy between liquid and solid state. You see, in this graphic, you can see the latent heat as a difference between in the enthalpy between liquid and solid. This one. So if we have the solid and we supply the heat, so the enthalpy will increase by interval AB from room temperature to the melting temperature, to the equilibrium melting temperature. And at this temperature, if we continue to supply the heat, so the temperature of the solid do not increase, but it converts from the solid state to the liquid state. So this heat, it is the latent heat of melting. Okay, and it's equal to the difference in the enthalpy between liquid solid. And after transformation from solid to liquid, from the point C, if we continue to supply the heat, so the enthalpy of the system of liquid, now it is liquid, will increase by interval CD. So it is the enthalpy curve of the system with the transformation from one state to the another. And correspondingly, we have the curve of the free energy. If the temperature increase, finally, at the beginning, the free energy of solid decrease until this temperature, and from this, the system exists as a liquid. So we have the curve of liquid continue from this point E to N. You see, it's a real free energy curve of system with transformation. With transformation. See the two energy curve and enthalpy curve. Enthalpy is also the energy. And here we have the solid, and higher than this temperature we have the liquid state, solid and liquid state. And, we should pay our attention to this equilibrium melting temperature. Very important feature of the system. So we have you can see the free energy. The free energy is a function of temperature, and it decreases with temperature. The higher temperature, the lower free energy. So we have this one like this. Okay, we have enthalpy curve of the system A, B, C, D, and the free energy curve of system A, E, F, A, E, F. If you magnify this one, magnify, enlarge this, and for simplicity we substitute the line, substitute the curve by the line for simplicity. So we have the curve of the free energy curve of the solid and free energy curve of liquid in red. In black. So at the melting temperature, they are in equilibrium. It means the free energy, their free energy are the same, are equal. Yes. In analyze this graphic, molar free energy versus temperature. So we have the free energy curve of liquid red, inferior curve of solid in black. So at this temperature, you have the reversible transformation, liquid to solid, and solid to liquid, because they are in equilibrium. So if some amount of solid transform to the liquid, so the same amount of liquid will transform into solid. So we have the reversible transformation. Reversible. Okay. Or we can say there are no transformation here. No transformation here. Because they are the solid and liquid are in equilibrium. So they can exist together at this temperature. Okay. So it Hello. Chào thầy đi nhé. So you see at this temperature, at this maintaining equilibrium temperature, the transformation is reversible. So how to make the transformation unreversible from liquid to solid only, and not in another direction, only from liquid to solid. It means unreversible transformation. So if the liquid is cool or undercooled by delta T, by some until to some temperature T, and T equal to Tm minus delta T. So we can say this liquid is undercooled by delta T below Tm before it solidifies. So in this temperature range, the system, the alloy, is still in the liquid state. So that is why we say that the liquid is undercooled until some temperature below this one. So if that the solidification will accompany with the decrease of free energy by delta C by joule per mole. See, temperature below this one, below the maintaining equilibrium temperature, we have the unreversible transformation only from liquid to solid, and the free energy will decrease by the amount of delta C. By the amount of delta C. See, because at T, the free energy of liquid is here, and free energy of solid is here. So it is the difference between the free energy of the two states. So if the free energy is decreased, the transformation is possible, and we have the transformation from liquid to solid only, but not from solid to liquid, because if the transformation from solid to liquid occur, so the free energy will be increased. It is impossible. The transformation can be possible only if the free energy decrease. Okay, so at this temperature, only transformation from liquid to solid is possible, but not from solid to liquid. Okay, and this difference in free energy is the driving force for solidification. Driving force. This free energy decrease, or the difference between the free energy, difference in free energy between the solid and liquid states is the driving force for solidification. Driving force. See, the free energy of system decrease. So we can calculate this decrease in free energy. So the free energy of the liquid is equal to enthalpy of liquid minus T multiplied by entropy of liquid. And free energy of solid equal to S. Enthalpy of solid minus temperature multiplied by entropy of solid. By this comes from the free energy equation. So at temperature T, this one, here delta C be equal to delta Sn minus Ss is a delta S, and T Sn minus Ss is delta S. So we have the delta C equal to delta T minus T delta S. Okay. This driving force for solidification. And this undercooling. You can see the driving force of for solidification is proportional to undercooling. The less undercooling, the greater delta C, the greater driving force. Okay. Okay. So at equilibrium, the free energy curve, the free energy of solid is equal. So we have delta C is 0. See? At this equilibrium temperature, the free energy are the same. So the difference is 0. So we have delta S minus Tm at this temperature, not this, at this Tm. Multiplied by delta S is 0. Okay. So from this, you can find that delta S is entropy of fusion. Entropy at this temperature is equal to delta S over Tm. So delta S it is the latent heat. So the delta SF is equal to ratio N over Tm. Okay. And we introduce one more thermodynamic term with the entropy of fusion. Entropy at temperature Tm. At this Tm. So this is known as entropy of fusion. Entropy of fusion. And the most pattern, this entropy of fusion is equal to the gas constant. The gas about 8.3 joule per mole per degree. So, now we know the entropy of fusion. So we have to note as small undercooling, if the delta T is small, the difference in specific heat can be ignored. So we can say that the specific heat of the liquid and solid are the same, are equal. If the undercooling is small. Okay. So in this case, we have the delta S, therefore it's approximately independent of temperature. Independent of temperature. Do not depend on the temperature. So you can combine these three equations. Delta C equal to delta S minus T delta S. And this equation, delta S is equal to M over Tn. We combine. And we substitute delta S is equal to L. And delta S, the difference in enthalpy is latent heat for melting. So we can have this equation. We substitute delta S by N and delta S by N over Tn in this equation. Have this. And we can rewrite like this. And finally, have the delta C equal to delta S multiplied by delta T. Physically, we can say the driving force for solidification, delta C, is proportional to the undercooling, delta T, and proportional coefficient is the entropy of fusion, delta S. See? So, the conclusion here, we can say the driving force for solidification is proportional to the undercooling. The higher, the lesser undercooling, the delta T, the lesser undercooling, the greater free energy, and the quicker, the faster the transformation can happen, can occur, can proceed. See? Because this is the driving force for solidification. So if the driving force is greater, so the proceed can occur, can happen quicker, faster, and because it's proportional to the undercooling, so the lesser undercooling, the quicker, the faster the process, the transformation. Because this driving force or transformation or solidification is proportional to the undercooling. Very, very important conclusion. Delta C equal to delta S multiplied by delta T. Now, the conclusion. You should remember this conclusion. Delta C, the driving force for transformation, is proportional to the delta T, to the undercooling. So our task to develop as large as possible the undercooling. So the transformation can, the crystallization process can occur faster, and more nuclei can form, and we have the final microstructure. It's the role, the sense of the undercooling. See? So the question: how much is maximum undercooling? How much is this delta T undercooling? The temperature range below the equilibrium melting temperature, but the system, the alloy, is still in the liquid state. In this temperature interval, the alloy is still liquid, not solid, not air. And only at T, the liquid transform to solid. It's the sense, the physical meaning of the undercooling. It's a temperature interval in which the liquid, the alloy, still as liquid state. It in temperature interval is below the equilibrium temperature, maintain temperature. Okay. So it is undercooling. So the question, how much is the maximum undercooling? How much? So in general, the maximum undercooling is 1/3 of the maintained temperature. 1/3. So for different metal, can have the different value of the undercooling. For example, for aluminum, the maximum undercooling is 195, for example. For iron, 295, and so on. For copper, 236. See? For example, for aluminum, the maintained equilibrium temperature of aluminum is 660 degrees. And if you can reach this undercooling, it means at a very low temperature, about 465 degrees. Aluminum is still in liquid state. Aluminum is still liquid, not solid. If you can reach, you can obtain this undercooling. Okay. And this maximum undercooling is obtained by metal atomization, by this process, atomization. And it's a need for homogeneous nucleation, atomization. The maximum undercooling can be obtained only by this process, atomization. Very large undercooling. See, the maximum undercooling for some metal. So, the next question, how the pressure can influence on the undercooling? Pressure. So we have the Raphaelian equation like this. Delta T is increase in undercooling because of the pressure over delta T is Km. It maintain equilibrium temperature, and with change in the volume, change in the enthalpy. This Lebron equation, and this effect is very small. The melting point of metal can be increased only by 10 power minus 2 degree per atmosphere. So if you can add 1 atmosphere to the liquid, so the melting point, melting temperature increase only by 0.01 degree. Very small effect. See? So, for example, we have example to estimate the change in equilibrium melting point of copper. This one. Estimate this delta Tp caused by the change of pressure delta P of 10 kilobar. 1 kilobar is equal to approximately equal to 1 atmosphere. Okay, see? If the pressure change by 10 kilobar. So how much? We change the melting point. Or you can we have to find this the undercooling caused by pressure. The molar volume of copper is 8 multiplied by 10 power minus 6 cubic meter for liquid and 7.6 for solid phase. The latent heat of fusion copper is 30.05 kilojoule per mole. The melting point of copper equilibrium melting point is 1085 degrees Celsius at normal condition. At the room and pressure and temperature. Okay. So you can apply this equation to find the change in the melting temperature delta T. Okay. So we have that here m delta S is equal to n to latent heat, and latent heat is here equal to 13,050 joule per mole. We convert to mole, to kilojoule, to joule, not kilojoule. Joule per mole. And then delta V here is volume of liquid minus volume of solid. Okay. And we have this. Here, 8 and minus 11.6. We have 0.4 multiplied by 10 power minus 6 cubic meter. Delta V. We have Tm. We convert to the Kelvin degree. So Tm is equal to this value plus 273. This is Tm. And delta P, finally, delta P is 10 kilobar. Delta P. And we convert to the Newton per square meter. 10 kilobar is equal to 10 power 9 Newton per square meter. So we substitute this value to this equation. You can find the delta T. Substitute this value in this equation. You can find delta Tp equal to 1 and equal to 42 degree Kelvin. It means here we have the very high. So it means about 0.0042 degree per atmosphere. Very small value, very small effect of pressure. If you increase on atmosphere of pressure, melting temperature change very small value. But here we have the 10 kilobar. 10 kilobar. Mean 10,000 atmosphere. Not on atmosphere. 10,000. Because by is equal to approximately equal to an atmosphere. Okay. So the melting temperature now is not this one, but plus 42 degree. So it now at 1,127 degrees Celsius at 10 kilobar instead of this one at normal condition. This is the effect of the pressure. But this increase on pressure is very less, very great. 10 kilobar is a very great change, very big increase in pressure. I mean about 10,000 atmosphere. 10,000 atmosphere. At the normal condition, we have the pressure is 1 atmosphere. But it is 10,000 atmosphere. So by increase pressure by 10,000 atmosphere, we can increase the melting temperature by 40 degrees. Only 40. See, the exam of the effect of pressure on the cooling on the melting temperature of the alloy. It's very easy to solve. So it's something on the single component system. But in the practice, we rarely apply the single component system. For example, we can use the pure copper to make the electrical wire like this. Maybe pure copper or pure aluminum. Is the case. We apply the single component system, or maybe pure iron to make the transformer, the core of the transformer. So you can see it is very rare cases. For electrical, maybe wire for core of the transformer. It is pure iron, pure copper, or pure aluminum. In practice, we apply the system not single component, at least two components. This is the binary solution. Binary. It means there are two components in this system, in this solution. Not single. Okay. So, but we will postpone this binary solution on the next lesson. Okay. Do you have any question? Any question? Hello? Who is any question?
Không ạ.
No question?
Yes.
Yeah.
Okay. I have upload the file. You see? Hello.
Yes, I see.
Okay. Thầy đã up cái file lên rồi nhé. Người có thể đọc thêm. Nay đang dừng ở đây nhỉ?
Dạ vâng ạ.
Ok. Goodbye.
Dạ vâng, em chào thầy.
Xin chào.
Goodbye, teacher.
Xin chào. Rồi, alo, Nguyễn Mai Nguyệt Quế vừa rồi đi đâu đấy? Em là gì đấy? Nguyễn Mai Nguyệt Quế á?
Vâng, em là Nguyệt Quế ạ.
Vừa rồi em đi đâu mà em vắng ấy?
Có cái khoảng từ 4 rưỡi đến 5 giờ là mạng em có trục trặc ạ. Thế nên là em bị out ra.
Lại mạng, lại trục trặc mạng. Ok. Bây giờ
Ok.
Ok, goodbye.
Goodbye teacher.
Em nhé.